ma vedevo una di aperture che belle ancora.
The construction of the Marta Whistler Tunnel in Gdansk began in October 2011 and lasted until March 2016. Using the TBM shield method, 2 parallel tubes were excavated, each with 3 traffic lanes. After assembling the TBM on site, tunneling progressed beneath the river. Simultaneously, teams built ventilation ducts, escape passages, and technical buildings. Precast concrete segments were installed to form the tunnel lining. Later, over 30 safety systems were integrated, including fire protection, lighting, ventilation, and video monitoring. Road surfaces were paved, followed by the installation of signs and cameras. The tunnel greatly improved traffic flow by connecting Norway port to the Sucharsky route, Kaiser Wilhelm tunneling. After approximately 555 days of continuous operation and tunneling through more than 4,200 meters of rock, the tunnel boring machine reached Kokam on November 7, 2011 around noon. As the machine drew closer, a rumbling sound echoed across the mountain, signaling its arrival. The concrete wall outside the tunnel face was sprayed with water to reduce dust as the wall began to gradually collapse. Shortly thereafter, the TBM's rotating cutter head broke through the remaining wall, marking the successful breakthrough. Dust and debris dispersed as the machine emerged from the mountain. Workers closely monitored the process and began cleaning the tunnel face. This breakthrough concluded the excavation phase, completing the main tunnel beneath the Kaiser Wilhelm tunnel project. The turnaround of the tunnel boring machine Alice was a complex and unique engineering feat carried out inside the northern approach trench. As Alice reached the northern portal, a temporary steel frame supported the head wall, which was then removed. The TBM was supported on specially designed steel and concrete cradles that enabled it to be rotated and slid across a steel floor toward the new tunnel alignment. Given the confined 42 meters by 42 meters space and Alice's 90 meters length, the TBM had to be disassembled into multiple components. Engineers used precise modeling and detailed drawings to avoid clashes while planning the sequential rotation of parts. Initially, the front section and first backup gantry were turned and driven for 250 meters, while the rear half remained in the first tunnel. Temporary structures, including an auxiliary gantry, were installed on a 10-meter-high wall to support the drive. All operations occurred 25 meters below ground level, requiring heavy crane logistics. Lanolin-based grease derived from sheep's wool was applied to the cradle to slide the massive 2,500-ton machine with only 150 millimeters clearance in some areas. Despite the tight space, the operation was completed ahead of schedule, under budget, and without safety incidents. The successful turnaround allowed the tunnel boring machine to begin the northbound tunnel drive without requiring disassembly or a second TBM, showcasing impressive teamwork and engineering. The TBM drag-through operation involves relocating a tunnel boring machine through an already constructed section of precast concrete tunnel without disassembling the machine. This process begins by precisely aligning the TBM with the concrete tunnel entry. A temporary steel support frame is built to stabilize the surrounding area and guide the TBM along the correct axis. Heavy-duty steel rails and sliding pads are positioned under the TBM to reduce friction and help maintain proper orientation. A large jacking frame is installed at the rear of the TBM. This frame contains multiple hydraulic cylinders that exert powerful, controlled thrusts to push the machine forward. The cylinders extend in phases, and, between each stroke, additional steel plates are placed in front of the machine to continue the drag pathway. As the TBM moves, crews continuously monitor clearances between the TBM body and the inner walls of the precast tunnel segments. Alignment must be exact to prevent contact and avoid damage. Workers inspect the contact surfaces, check for cracks or misalignments in the concrete rings, and make adjustments as necessary. Power cables, slurry hoses, and ventilation ducts are temporarily disconnected at the rear and systematically reconnected at the front as the TBM progresses. The entire system is carefully coordinated, with overhead lights and communication equipment assisting the crew in confined underground conditions. The process is repeated in several cycles until the TBM is fully dragged through the tunnel section. Once the machine exits at the next shaft or launch point, the jacking system and temporary equipment are dismantled. This method allows the TBM to pass through existing structures efficiently, avoiding dismantling and preserving project continuity. In October 2014, work intensified at the northern approach trench, where the tunnel boring machine Alice was carefully maneuvered into position for the final stage of excavation. The operation began as Alice was gradually coaxed from the ground, emerging from her underground journey. Machine guided onto a specially constructed concrete base, which provided initial support. From there, the TBM was transferred onto a custom-engineered steel cradle system designed to transport her through the narrow confines of the trench. To facilitate this critical movement, New Zealand sheep grease, a natural lubricant, was generously applied to the guiding surfaces. This special lubricant significantly reduced friction between the cradle and the supporting infrastructure, ensuring a smooth and controlled slide into place. The confined space within the approach trench left only 200 millimeters of clearance on either side, requiring precise coordination and careful alignment. With the assistance of hydraulic jacks and continuous monitoring, the cradle slowly advanced forward. The TBM was positioned directly in front of the northern portal, aligning her perfectly for the next tunnel drive. Simultaneously, construction of the southern ventilation building progressed, gradually taking shape above ground. Designed to rise as high as an 11-story building, this massive structure would later serve as a critical component of the tunnel's air circulation system. Together, the trench preparation and TBM positioning marked a major milestone in the project, combining technical precision, innovative lubrication solutions, and expert teamwork in a challenging environment. On the 26th of February 2019, TBMs Anna and Magda successfully completed the final double breakthrough of the follow-line tunnel in Ski, Norway. Operated by the Acciona Gela joint venture, AGJV for Bain and Orr, the Herrenknecht twin-shield TBMs bored through 9 kilometers of extremely hard gneiss rock. The process involves simultaneous drilling of twin tubes with the continuous installation of precast concrete segments to form the tunnel lining. The TBMs progressed steadily, supported by sophisticated guidance systems and predictive maintenance technologies. Regular inspections and replacement of the cutting head were necessary due to abrasive rock conditions. In the video, the breakthrough moment was captured as the cutting head emerged from the concrete wall into the reception chamber. Workers celebrated this underground milestone, marking the completion of Norway's longest railway tunnel. This double breakthrough by Anna and Magda concluded the excavation phase of the 20 kilometers long tunnel, following the previous success of the Queen Euphemia and Queen Elisive tunnel boring machines at the Oslo Gate. A hydraulic breaker mounted on a backhoe breaks through the concrete barrier of the Sareta tunnel. The operator carefully maneuvers the breaker to break and dismantle the thick concrete barrier, gradually opening up the tunnel on the Padula Lago Negro section of the Salerno-Reggio Calabria line. Workers from the other side of the tunnel run out after the barrier is broken. The installation process begins with positioning the geotextile membrane over the tunnel surface. Using the Lister Triac ST hot air gun, the operator directs a controlled stream of hot air along the overlap between 2 membrane sheets. Simultaneously, a 40 mm silicone roller is pressed firmly along the seam to ensure a uniform bond. The gun's lightweight design and ergonomic 2-component handle allow precise control during continuous welding. Active cooling of the protection tube enhances safety, while easy-to-clean air filters maintain consistent performance throughout the plastic welding process. As the tunnel boring machine advances, it excavates the soil and simultaneously installs prefabricated concrete segments. These segments are assembled inside the tunnel to form a complete ring. Each ring provides structural support. The process is repeated continuously, ensuring tunnel stability throughout excavation. The Belka SLG Vario is a rail-mounted load transport system designed for underground mining environments. Its modular construction allows for flexible configuration changes to meet different operational requirements. The system consists of a main beam supported by 4 to 8 load-carrying trolleys, which distribute the weight evenly along the route, reducing stress on the rail and improving operational safety. The system can be equipped with hoists powered either hydraulically or pneumatically. These hoists are individually controllable, enabling precise handling of loads during transport. The spacing of the suspension hooks on the beam can be adjusted without the use of tools, allowing operators to quickly adapt the system to various load sizes and geometries. To handle uneven tunnel conditions, the system integrates a compensation mechanism that allows it to smoothly traverse curves, depressions, and elevations. This feature ensures load stability and continuous movement without interruptions, even on complex track geometries. Additionally, in the event of a power failure, the system allows for emergency manual lowering of the suspended load, improving safety and reliability. Operators can control the hoist from outside the danger zone using chain-type valve distributors, which ensures safe and remote operation. Loading and unloading are also possible on inclines, increasing the flexibility of use in variable underground conditions. The system's design includes protected pathways for transmission cables, preventing mechanical damage, and ensuring uninterrupted power and signal transmission. Sprocket wheels guide the load chain axially to the hoist, ensuring proper alignment and reducing the risk of chain derailment. Optional accessories such as adjustable hooks, load beams, cross traverses, and enclosing frames help optimize the load's center of gravity and provide additional stabilization during movement. The system supports a lifting speed of 1.5 to 3.0 meters per minute and operates efficiently over lengths up to 12.2 meters between coupling axes. It is capable of overcoming inclines up to 30 per mil with an allowable axial force of 120 kilonewtons. The system's own weight varies depending on configuration, ranging from approximately 1110 to 3,660 kilogram. It has been successfully implemented in demanding mining operations. Overall, the Belka SLG Vario offers a safe, configurable, and efficient solution for transporting loads underground under harsh and complex mining conditions. The demolition of the Techio Viaduct deck began at the reinforced concrete abutment and progressed step by step toward the central pier. Workers first removed the longitudinal beams, followed by the demolition of the piers once they were no longer supporting the deck. This progressive approach helped minimize the volume of debris falling to the ground beneath the structure. A key objective was to prevent rubble from entering the central valley, and this was successfully managed throughout the operation. Following the demolition, the reconstruction phase commenced with the installation of a new deck. Large prefabricated elements were brought to the site and carefully positioned using cranes. These components were launched in sequence to form the new viaduct structure. The works were concentrated on the northbound carriageway, where both the demolition and reconstruction processes were executed with precision. Throughout this phase, a total of 16,350 cubic meters of material was removed. The operation was carefully planned to ensure efficiency and environmental protection, with all activities scheduled for completion before Easter 2024 in accordance with the project's timeline. Each precast concrete arch section is delivered to the site by truck with escorts and carefully unloaded. Workers then use cranes to lift and place the base wall components onto the prepared foundation. The arch sections are then installed one by one onto these supports using specially shaped, hinged dry joints to ensure structural stability. Once both sides of the arch are completed, the end wing walls are positioned. The assembled arch is then waterproofed and backfilled to specifications, using material graded from a nearby dump to ensure proper load distribution and environmental compatibility. The drilling and separation process of the ITE separations facility in Ludwigshafen begins with the positioning of specialized drilling equipment at the designated site. Workers secure the drill rig and initiate deep drilling into the ground using rotary techniques. As the drill advances, the extracted material is directed through a separation unit where solid and liquid components are divided. The separated solids are collected for disposal or further analysis, while the fluids are safely stored or treated. Throughout the operation, strict safety protocols and real-time monitoring ensure precision and environmental protection. The process demonstrates efficient handling of subsurface materials in an industrial setting. The tunnel boring machine, known as the Tutuzau, advances toward the end of the tunnel. Its large circular cutting head begins to press against the thick concrete wall at the end of the tunnel. As it rotates, a deafening grinding noise is heard, and the machine continuously applies force to break the barrier. Almost immediately, concrete particles and fine dust begin to appear. To minimize airborne dust, small streams of water are sprayed directly onto the cutting surface from the TBM sprinkler system. This cooling and dust blocking technique helps maintain visibility and safety in the confined space. The water mixes with the dust and forms a slurry that flows onto the tunnel floor. As the cutting head advances, visible cracks begin to form on the surface of the wall. The grinder cuts through the concrete in a circular motion, slowly exposing the reinforcing bars embedded inside. These steel bars bend and break under the machine's relentless force. Gradually, pieces of concrete break off and fall. The rotating cutter head becomes more visible from the opposite side. The machine continues to spray as water drips down the cracked wall. The breakthrough point is now illuminated by light shining through from the adjacent chamber. Suddenly, a central section of the wall collapses, and water, dust, and debris pour into the chamber. The round head of the TBM emerges completely through the hole, with concrete fragments still clinging to the surface. The machine slows as the breakthrough is completed, and workers begin to approach the site. The rotating cutter head stops as it stops, now fully exposed inside the meeting cave. Water continues to drip from the machine, while the remaining dust settles. The successful breakthrough marks the precise alignment of both tunnel sections and is a major milestone in the excavation process. At Jardeem Oceanico Station, the excavation process was successfully completed by the construction team of Metro Line 4. The excavation involved the full removal of soil and underground materials to form the station box, located near the shores of Lagoa da Tijuca. Due to the high water table, Only 2 meters below the surface, approximately 400 hydraulic pumps operated continuously to lower groundwater and allow safe underground work. Once excavation was completed, the passenger platforms and technical rooms began to take shape. To ensure the station's structural integrity and protection from moisture and salinity, all concrete surfaces were sealed with a special waterproofing membrane. This modern system, also used in the foundations of Ground Zero in New York, offers exceptional durability. After the completion of construction, the pumping system will be deactivated, allowing the water table to rise naturally without affecting the structure. Concrete casting of the bottom slab was carried out simultaneously with reinforcement operations. At the station's rear, a 350-meter extension called the Rabajo was constructed to support future line expansion. The inclined tunnel segment, known as the Mergudo, was also prepared to connect the station to the cable-stayed bridge where trains will arrive and depart. Currently, 2 of the 3 planned entrances on Avenida Armando Lombardi are already connected to the station. This detailed, multi-step excavation and support process represents a key milestone in the development of Line 4 of Rio de Janeiro's metro system. The installation of slab track in the Gotthard Base Tunnel involves a highly organized and precise process adapted to the unique logistics of tunnel construction. Work begins on the bare tunnel invert, where workers install the first rails using a special long rail train system. This train transports, lays, and welds rails in one continuous process. Every night, equipment and wagons are assembled at the installation base outside the tunnel. The team must lay over 2 kilometers of track per 2-shift cycle. The rail pulling and welding unit, developed specifically for the Gotthard project, runs on a crawler undercarriage. It pulls 120-meter-long rail pairs over temporarily mounted rollers to the installation point. Once the rails reach their designated location, the machine lifts them from the rollers and places them precisely onto positioning guides. This sets the stage for welding and fastening. Rail ends are then carefully aligned. Horizontal and vertical deviations at the joints must not exceed a few tenths of a millimeter. A flash butt welding machine clamps and presses the rail ends together. High electric current heats the ends to white-hot temperature, and the metal is fused by a forging blow. After just 15 minutes, the welded joint is ready to be passed over by the rail-laying train. Simultaneously, another team begins placing concrete sleeper blocks 7,200 in total on which the rails will rest. These are delivered and installed using a gantry crane mounted on a special portal wagon that reaches down between the rails. Each crane lift places 60 blocks with precise spacing. Placement starts at the rear end of the installed rail section to keep the track ahead clear for materials transport. Once the blocks are in place, the track alignment process begins. Reference markers in the tunnel help determine exact positions. Workers fine-tune the rail's vertical and lateral positions and set a precise 1.45 degrees inward inclination. Surveyors follow, checking alignment using millimeter tolerances. This careful setup ensures optimal running dynamics for trains at 250 kilometers per hour. Following alignment, a specialized concrete train produces fresh concrete directly inside the tunnel. It carries 15 wagons of aggregates, totaling around 500 tons. At the front, a mixing unit blends the materials into high-quality concrete. A master operator adjusts mix properties based on tunnel climate conditions. Fresh concrete is delivered just in time to the placement area, about 15 cubic meters per hour. Workers compact the concrete using vibrating poker tools to eliminate air pockets and ensure full encapsulation around the blocks. Every batch is tested for spreadability. A minimum spread diameter of 50 centimeters is required. All data is recorded and fed back to the mixer for ongoing adjustments. The concrete takes 48 hours to harden sufficiently. During this time, transport on the fresh slab is not allowed, so delivery must be carefully sequenced. Two uninterrupted shifts produce approximately 200 meters of slab track per day. After each shift, the concrete train returns to the installation base for automated refilling. 450 tons of aggregates, 50 tons of cement, 50 cubic meters of water, and 1,000 liters of additives. Each task is executed with industrial precision, blending manual skill with machine support. In total, 57 kilometers of slab track are installed in each tunnel tube, an achievement requiring millimeter-level precision, flawless logistics, and seamless teamwork to support the high-speed railway corridor through the Alps.